Hello everyone, welcome to our Nature Academy. Myself Dr. Shaik Ahmed. In this video, we are going to discuss the third postulate of quantum mechanics. The third postulate talks about the measurements and eigenvalues of the system. So in the previous two lectures, we have discussed the first postulate and second postulate. You know that the first postulate is related with the state of the system, and the second postulate talks about the operators of the system. What is an operator? Operator is nothing but a mathematical rule which applies to state of the system. It can take to another state. According to the second postulate, every measurable physical quantity is associated with an operator. Now the third postulate connects the first and second postulates. So we'll discuss the third postulates in this lecture. In quantum mechanics, the act of measurement generally perturbs the state of the system. In quantum mechanics, the act of the measurement generally perturbs the state of the system. When you do some measurement on a system, the system will change its state. So that is the third postulate of quantum mechanics. In classical mechanics, we can find this type of perturbation, but the perturbation is very less. It is negligible. While carrying out measurements on classical system, this perturbation does exist, but is negligible. So here the point is the act of measurement on any system will change its state. So let us have some examples here. The first example, I will take hot water in a beaker and I want to do some measurement on this hot water. That means I want to find the temperature of the hot water. So this is a beaker and there is a hot water in this one. Now I want to find the temperature of this hot water. So I want to do some measurement on this hot water. So how will you find the temperature? For this I need to use a thermometer. So I assume that initially the thermometer, this is a mercury in glass type thermometer, and this is maintained at room temperature 27 degrees centigrade, and the hot water is more than 27 degrees temperature. When you plunge this thermometer into this beaker, there is a heat transfer between the hot water to this cold thermometer. When you compare the temperatures, the hot water in the beaker is hotter body and the thermometer will be a colder body. Since the temperature is here in the beaker is more than 27 degrees and the thermometer is at room temperature, which is at 27 degrees. So there is a heat transfer from hot water to this cold matter thermometer. I can say that there is a small disturbance in the temperature of this hot beaker. For example, the actual value, assume that the actual value of the hot water, the actual temperature of this hot water is, assume that it is 68.95 degrees centigrade. Assume that this is the temperature actual, but because of this thermometer, because of this cold thermometer, there may be a small difference in the temperature value. You can see this is 68.90 degrees. The 0.5 degree may be transferred to this thermometer. Okay, so here my point is, when you do the measurement on some system, the state of the system is changing. When you try to find the temperature of the hot water in a beaker, some of the temperature is transferred to this cold thermometer. So this is one example for the third postulate of quantum mechanics. The act of measurement generally perturbs the state of the system. Now I will take another example. For example, I want to find the location of an hydrogen electron. If you take an hydrogen atom, around this nucleus there is one valency electron moving around this one. Now I want to find the position of this electron. What is the radius of this electron? What is the radius of this orbit? Generally the radius is in the order of 10 power minus 10 meters. Now if you want to find this electron, you should use a photon of wavelength which is approximately equal to the size of the orbit, that is 10 power minus 10 meters. To locate this electron, we must use a detector. Here a detector is my photon. When you bombard this photon on this electron, you can find the location of the electron. So what is the wavelength of the photon? You should use a photon of wavelength approximately equals to 10 power minus 10 meters. Then find the energy of the photon. So energy of photon is hc by lambda. Substitute h value, c value here and lambda value. You will get the energy of the electron is in the order of 10 power 4 electron volts. When you substitute H value, C value and lambda value, you will get the photon of energy 10 power 4 electron volts. That means to bombard this electron, we should use a photon of energy 10 power 4 electron volts. If you use a photon of this energy, the electron get ejected from this orbit. We know that the ionization energy of an electron in hydrogen atom is 13.6 electron volts. We know that the ionization energy for electron in hydrogen atom is 13.6 electron volts. What do you mean by this one? If you use some energy which is equal to 13.6 electron volts, you can easily remove the electron from the atom. 13.6 is very less when compared with 10 power 4. So if you want to locate the electron with the help of a photon, that means you are trying to do some measurement on this electron, then the electron will change its state. It will be removed from this state, right? Since the ionization energy is 13.6, if you use any energy more than 13.6, the electron will come out from this orbit. That means the state of the system is changing. So this is another example for the postulate 3, the quantum mechanics. So here I am going to conclude the postulate 3, that is the state of the system will change if you do some measurement on the system. One example is measure the temperature of hot body here, and another example is electron inside an atom. So if you want to find the electron, the state of the electron may change. Next, we can represent the measuring device by an operator. Just now we saw that I have used a detector to find the position of the electron. In quantum mechanics, the detector can be replaced by an operator, so that after carrying out the measurement, the system will be in one of the eigenstates of the operator. The example for detector is a CCTV camera, right? CCTV camera is one detector, so which captures the photons. So in quantum mechanics, this detector can be represented with an operator A cap. So when you perform some measurement on the system, generally the system will be represented with, the state of the system will be represented with a wave function, and the detector is represented with an operator. So A acting on psi is nothing but the measurement on the state psi. What is A here? A is an operator. In our words, we can say that A is nothing but a measuring device. In mathematical words, in mathematical sense, I can say the operating is nothing but a mathematical rule. So when you do performance, when you do some measurement on the state of the system will be in one of the eigenstate of the operator, and that is, I can write the wave function psi is equals to the linear combination of all eigenfunctions with an. So what is eigenfunction or eigenstate? I will discuss here. So a state vector psi is said to be an eigenvector of an operator A if A operates on psi. You will get a constant value A into psi, where A is a constant value. It may be a complex number or it may be any real number. Generally A will be a complex number. If it is the operator A is a Hermitian, then you will get a real number, otherwise a complex number. The constant value is known as eigenvalue, and psi is known as eigenvector. If you do some measurement on the state of the system will be in one of its eigenvalues. It may be like A1, it may be like A2, it may be like A3, A4, A5, and psi1, psi2, psi3. It may be in any one of eigenvectors. This equation is known as eigenvalue equation. There are some properties of eigenvalue equations. This is eigenvalue equation. Operator A acting on psi will give you small a eigenvalue into eigenvector psi. So this equation is known as eigenvalue equation, and it has some physical significance. So this is a mathematical representation of measurement of a system. So this is eigenvalue equation. A power n on psi will be small a power n on psi. That means if you do measurements repeatedly, one time, two times, three times, if you do the measurement n times, you will get the eigenvalue equation like this. The eigenvalue will be a power n. And there is another property. So if the system satisfies this equation, eigenvalue equation, A acting on psi, then any function of operator A, function operator acting on the wave function psi, will be equals to function of eigenvalue into psi. If this eigenvalue equation is satisfied, then I can also write like this. For example, A is acting on wave function psi like this, then what will be the eigenvalue of this function? Here e power A A is an operator, right? So e power A is a function operator. I can write like f of A is acting on psi. Then what will be the eigenvalue of this function? Use this formula. F of A acting on psi will be equals to f of eigenvalue A. Then I will simply write e power A. So this is eigenvalue equation for this e power A. There is one more property, that is eigenvalues of an inverse operator. If you know this eigenvalue equation, A is acting on psi, and I will write like this eigenvalue equation, then A power minus 1, the inverse operator acting on psi, will give you 1 by A into psi. Here 1 by A is, I can also write like this, A power minus 1. So inverse operator will have the inverse eigenvalues. So let us try to solve one problem. This question appeared many times in GATE exam and Central Universities exams. The operator x plus d by dx has the eigenvalue alpha. Determine the corresponding wave function. So if you want, you can write the operators with caps also. For simplicity, I removed these caps. There is an operator which has eigenvalue. So what is general eigenvalue equation? A psi, you can write like this also, alpha psi. If you want to use the ket notation, you can use, otherwise you can ignore that. So this is eigenvalue equation. In this problem, he has given that there is an operator which has eigenvalue. Now find the psi value. So what is operator here? X plus d by dx is given, which is equals to alpha into some eigenvalue. Let us say the eigenvalue is psi. Okay. Let me call the eigenvalue is psi. You want to use, you can, if you want to use the ket value, you can use, or simply you can write psi itself. So let us expand this one. So this is x plus x into psi plus d by dx into psi is equals to alpha into psi. Now take this term on this side. So here you will have d by dx into psi is equals to alpha minus x into psi. So I will use variable separable method, that is d psi by psi is equals to alpha minus x into dx. I will write like this. My aim is to find psi. What is the psi value? So here I am trying to find psi value, therefore I will integrate on both sides. The integration of 1 by psi into psi will be log psi with the base e. On the right side, the integration of alpha dx, you will get x only, x into alpha, and integration of x is x square by 2. Okay, plus the constant term, I will write log psi naught. This is my constant term. So when you simplify this one, the psi value is nothing but psi is equals to psi naught into exponential alpha x minus x square by 2. So this is the required wave function of the given operator x plus d by dx. So there is another question in GATE 2003. A particle has a wave function psi of xt, a e power I omega t cos kx. Which one of the following is correct? This is an eigenstate of both energy and momentum. This is an eigenstate of momentum but not energy. This is an eigenstate of energy, not momentum. And this is not an eigenstate of both energy and momentum. Let's try to find the solution. Given that psi of x comma t is equals to a e power I omega t cos kx. So first you must know the operator, energy operator. What is energy operator? Energy operator E can be written as IH bar dou by dou t. On this side I will write momentum operator. Momentum operator is minus IH bar dou by dou x. So what is eigenvalue equation? Generally eigenvalue equation is A psi is equals to some alpha into psi. Here A is operator, this is also operator, this is also an operator. So this is the eigenvalue equation. So now let us check whether the wave function given here is an eigenfunction of energy or not. So let us try to write E psi like this, that is IH bar dou by dou t of given wave function a I power omega t cos kx. So this is the derivation with respect to time t. I will write IH bar cos kx, and a is also there, so I will write a here. So derivative of e power I omega t is e power I omega t into I omega. I into I, you get minus 1, and there is a h bar omega e power I omega t and cos kx. And I will write this one as minus h bar omega a into e power I omega t cos kx, that is nothing but psi. So this is in the form of the eigenvalue alpha into psi. So what is eigenvalue here? Minus h bar omega is eigenvalue, and the given psi is in eigenvalue form. E psi is equals to alpha psi. That means the given wave function is an eigenfunction of energy. Now let us check the momentum operator. So now I want to check p psi is equals to alpha psi or not. So minus ih bar dou by dou x of psi. So here the differentiation is with respect to x. So take the time dependent terms outside. So this is minus ih bar. A is a constant and e power I omega t is also constant here. And derivative of cos x is minus sin x. This is minus sin kx. There is a minus sign here, and there is a k term also. So now there is a minus into minus plus. I h bar k is there, and a e power I omega t and sin kx, and this is not equals to your alpha psi. So this is not a wave function psi. That means p psi is not equal to alpha psi. So this is not a wave function. So psi is not a wave function of, the psi is not an eigenstate of the momentum operator. If you write p psi is equals to alpha psi, then I can say the given wave function psi is an eigenstate of the momentum. But here what we get, p psi is not equals to alpha psi. So I can say that it is not an eigenstate of momentum. It is an eigenstate of energy but not of momentum. So option 3 is the correct option. So there is another question in GATE 2003. Given that A operates on psi 1 gives you psi 2, and A operates on psi 2, you will get psi 1. Which of the following are eigenfunctions of an operator A square? Whenever you see the eigenvalue equation, whenever you see this type of question, first of all write down the eigenvalue equation. So what is eigenvalue equation? Eigenvalue equation is A operating on psi will give you some, let us say the eigenvalue is A into psi. So this is eigenvalue equation, right? In this problem, he is given A operating on psi 1, you will get psi 2. Now he is asking which of the following are eigenfunctions of A square. Operator A square acting on psi 1 is simply A acting on A psi 1. So when A is acting on psi 1, you will get psi 2. And A acting on psi 2 is nothing but psi 1. And I will write this one as 1 into psi 1. So check this equation, A square and psi 1, you got 1 into psi 1. So here eigenvalue is 1. Eigenvalue is equals to 1 for eigenvalue is equals to 1 when A square is operated on psi 1. That means when you do the measurement twice on the state function on the eigenstate psi 1, you will get eigenvalue 1. What do you mean by eigenvalue? Eigenvalue is nothing but the result of the measurement. When you do some measurement on the system, you will get some result, right? That result is nothing but eigenvalue here. So similarly, operate A square and psi 2. So that means psi 1 is an eigenstate of A square. It is clear from this one, right? Psi 1 is an eigenstate of A square. Let us check psi 2. When you operate A square and psi 2, I can write like this, A into A operating on psi 2, and A on psi 1 is psi 2. So you will get psi 2 again here, and this is nothing but 1 into psi 2. So 1 is the eigenvalue here, and this is in the form of eigenvalue equation. Therefore, I can say that psi 1 and psi 2 both are eigenfunctions of A square since they are obeying eigenvalue equation. So option A is the correct option. Next, there is a question in CSIR 2015, that is in December. A Hermitian operator O has two normalized eigenstates with eigenvalues 1 and 2 respectively. The two states u is given here, v is given here, such that there is a condition and there is another condition, orthonormal condition is given. Which of the following are possible values of theta and phi? First of all, write down the given conditions. He said that there is an operator, Hermitian operator. Hermitian operator is nothing but when a O dagger is equals to O, this is Hermitian operator. When it is operating on eigenstate 1, you get eigenvalue 1, and this is an eigenvalue equation. And when this operator is acting on state 2, you will get eigenvalue 2, and this is the eigenvector. So this is the condition he has given. In addition to these two conditions, he gave u value. The ket vector u is given by cos theta 1 plus sin theta, the state 2, and v is given. This is cos phi and the state 1, and this is sin phi, state 2. And there are two other conditions also given. Operator O acts on v, what will you get here? So cos phi, and this is 1, sin phi, state 2. The first one is cos phi. When O is acting on the state 1, what is the eigenvalue? You will get eigenvalue 1. So I will write the state as it is. When O is acting on state side 2, when O is acting on second state 2, first write down the sin phi value. O is acting on 2, you will get 2 into state 2. Since 2 is the eigenvalue of this operation. Now try to operate a bra vector on this operator O, then we'll get there is a 1 and cos phi plus 2 bra vector 2 and sin phi. This is acting on this one. Okay, so that is cos phi 1 plus 2 sin phi state 2. Since 1 and 2 are orthogonal, or they are orthogonal states, so you will get here this one into this one, that is cos square phi into 1 plus the scalar product 1 into 2 is 0. The scalar product 2 into 1 is also 0, since they are orthogonal states. So we will get only the scalar product of 1 and 2 and 2. So this is one thing, cos square phi. Another one is this one and this one. You will get 2 into sin square phi, right? So here this is scalar product 2 into 2. And I will write this one as cos square phi plus 2 sin square phi is there. So I will write sin square phi plus sin square phi. So I am writing this 2 sin square phi as sin square phi plus sin square phi. This is 1 cos square theta plus sin square theta. Cos square phi plus sin square phi is 1, and this is sin square phi. That is 1 plus sin square phi is there. So which is given that it is 7 by 4 from the equation 1. From the condition 1, this operator is given by 7 by 4. So equate with 7 by 4. From this you will get sin square phi is equals to 7 by 4 minus 1. You will get 3 by 4. From this I will get sin phi is equals to root 3 by 2. And if I want to write phi value is 60 degrees or pi by 3. So to find the theta value, use the second condition. What is the condition? The orthonormal condition, u into v is equals to 0. So here u is, it's simply 1. You can write cos theta here and sin theta here, and the state vector 2 here. This is u, and v is cos phi state vector 1, and this is sin phi state vector 2, so which is equals to 0. So here you will get cos theta cos phi from the first two terms, and from these two terms you will get sin theta sin phi, which is equals to 0. The remaining terms are zeros, since the states are orthonormal. Orthonormal means when you have states like this I comma j, this is delta ij. When I is equals to j, then you will get 1, otherwise it is 0. So cos theta cos phi plus sin theta sin phi is equals to 0, and I will write this one as cos of phi minus theta, cos of a minus b. I will write it as cos of phi minus theta, which is equals to 0. So cos 0 is nothing but cos pi by 2. So from both sides I will write phi minus theta is equals to pi by 2, or theta can be written as phi minus pi by 2. Phi is pi by 3. We got phi value as pi by 3. So here you will get minus pi by 6. What is the answer here? Minus pi by 6. So phi is pi by 3 and theta is equals to minus pi by 6. So option A is the correct option. Moving on to the next problem. This problem appeared in JEST 2012. The wave function of a particle in one dimension is given by psi of x is equals to a sin x plus b sin 3x. Then psi of x is an eigenstate of the position operator, the momentum operator, the Hamiltonian and the parity operator. So you remember that the position operator x, when operates on a wave function psi of x, you will get like this. So when this position operator is operating on psi of x here, that means x is operating on a sin x plus b sin 3x. You will get x into this value as it is, a sin x plus b sin 3x. So this is not an eigenvalue equation. Eigenvalue equation means you will get an eigenvalue that is constant eigenvalue. But here x is a dependent variable. So psi is dependent on x. So you cannot have x as an eigenvalue. That's why the position operator, that's why the wave function psi is not the eigenstate of position operator. Now let us check the momentum operator. So momentum operator is given by p cap is minus ih bar dou by dou x. So operated on psi, you will get minus ih bar dou by dou x a sin x plus b sin 3x. So you will get minus ih bar, a sin x will become a cos x and b sin x will become b cos x, and there is a 3. So 3b cos x, and this is not equal to the wave function psi. The eigenvalue a into wave function psi, since the wave function has been changed to cos terms. Initially it is sine, you now it changed to cos. So this is not the eigenstate of momentum operator. Similarly, you can check for the Hamiltonian. The Hamiltonian is an operator. Generally, we'll write minus h square by 2m del square. Del square is nothing but dou square by dou x square. When you differentiate the wave function psi twice, you will get some other wave function. So psi of x is not an eigenstate of Hamiltonian. You can check this one. And the last one is the very important one, the parity operator. So what is parity operator? I will explain here. If parity operator is acting on wave function psi of minus x, it can be written as psi of x or it can be written as minus psi of x. If you write parity operator is nothing but the inversion operator, inversion about the origin. So when you operate an inversion operator on psi of minus x, if you get psi of x, this is even parity. Even parity, and the operator is known as even parity operator. If you get minus psi of x, this is known as odd parity, or the wave or the operator is known as odd parity operator. Now here the wave function is like this. The given wave function is psi of x, a sin x plus b sin 3x. If you change psi of x as psi of minus x, here you will get a sin minus x plus b sin minus 3x. So take the minus outside, you will write minus into a sin x plus b sin 3x. This is nothing but minus psi of x. That means the given function is an odd parity operator. Therefore, psi of x can be stated as the eigenstate of the parity operator. So the answer is the parity operator. So here I want to give some hints. The momentum operator, if you want to say any wave function psi is an eigenstate of momentum operator, then the eigenstate must be is in the form of e power ikx. Plane waves. The wave function representing a plane wave is an eigenstate of momentum operator. This is an hint. You can call it as trick or hint. Any wave function describing in the form of a plane wave is an eigenstate of momentum operator. Then what about position operator? This is about momentum operator. For position operator, the wave function must be in the form of Dirac delta function, like this. If the wave function is in the form of Dirac delta function, then I can say that that given wave function is an eigenstate of position operator. If you apply position operator, if you operate the position operator on the wave function psi of x like this, you will get x1 into delta minus x1. When x is equal to x1, you will get the value. So for position operators, the wave function should be in the form of Dirac delta function. Then only we can call this as the given wave function is an eigenstate of position operator. For momentum operators, the wave function must be in the form of plane waves. For position operator, it must be in the form of Dirac delta functions. For parity operators, if you get psi of minus x is equal to psi of x, that is even parity, or if psi of minus x is equal to minus psi of x, that is odd parity operator. There is another interesting question. If psi q is any eigenstate of electric charge operator q corresponding to eigenvalue q, which is given like this, given that q acting on psi of q is eigenvalue q into psi of q. So electric charge operator. So charge is a measurable quantity. So I can associate an operator for this charge. So here q cap is the operator representing the electric charge, and it is following the eigenvalue equation like this. The charge conjugation operator C is there, and when C is operating on the wave function psi of q, so it is changing into psi of minus q. This is charge conjugation operator. And when when q is operating on psi of minus q, you will get minus eigenvalue q into psi of minus q. These are the given conditions. Now what is the question here? Find the eigenvalues of the operator CQ plus QC. Can a state simultaneously be an eigenstate of C and Q? First of all, I will start with A. CQ plus QC. I can also write it as C comma Q. Poisson bracket. Anti-commutator. When this operator is acting on a wave function psi, here the psi is psi of q, then we will get on the right side, the first term is acting on psi of q, then you will get, when q is acting on psi of q, you will get q into psi of q, plus here c is acting on psi of q. When c is acting on psi of q, you will get psi of minus q. Next, take q outside here. When c is acting on psi of q, you will get psi of minus q, plus when q is acting on psi of minus q, here is given that q is acting on psi of minus q, you will get minus q. So remove this one. This is minus q into psi of minus q. So this is plus q psi of minus q, and this is minus q psi of minus q. So you will get 0. Therefore, I can write the Poisson bracket, I will call this as are anti-commutators, is equals to 0. Therefore, I will say C and Q do not commute. C and Q do not commute each other. The value CQ plus QC is nothing but the anti-commutator C comma Q. Now operate this one on a wave function psi of Q, then you will get this one. When Q is acting on psi of Q, this is the thing. This is eigenvalue equation for Q acting on psi of Q, and this is the eigenvalue equation for Q acting on psi minus Q, and this is the eigenvalue equation for charge conjugation operator C. So use these eigenvalue equations here, you will get CQ plus QC is equals to 0. So CQ plus QC is nothing but anti-commutator 0. That means C and Q do not commute each other. When C and Q do not commute each other, we can't find simultaneous eigenvalues. We cannot find simultaneous eigenvalue. Can a state simultaneously be an eigenstate of C and Q? So the answer is no. So here the value is 0. They anti-commute each other. When they anti-commute each other, we cannot find simultaneous eigenvalues. If they commute, then we can find that the eigenvalue of C and Q, then we can say that the C and Q commute each other and they will have simultaneous eigenvalues. And there are some points to remember. These are very important points. For a Hermitian operator, all its eigenvalues are real and the eigenvectors are orthonormal. We can prove this one also. And I don't want to go into the derivations or the proof for this one. You can find the derivation in any book. Next, the Hermitian operator is diagonal in orthonormal basis with its diagonal elements equal to eigenvalues. This basis set is unique if the operator has non-degenerate eigenvalues. It is not unique if there is a degeneracy. Degeneracy is nothing but eigenvalues have same eigenstate having same eigenvalues. Non-degenerated eigenvalues means different eigenvalues. For different eigenvalues there are different eigenvectors. For example, lambda 1 has one eigenvector and lambda 2 has another eigenvector like this. If we have different eigenvalues, we will have different eigenvectors. If two operators that are Hermitian operators A and B, we can construct a common orthonormal basis and that is made up of the joint eigenvectors A and B. If there are two Hermitian operators, they will commute. If they commute, we can form a common eigenvectors. The eigenvalues of anti-Hermitian operator are either purely imaginary or equal to 0. You can also prove this one. You can find the proof in any book. The eigenvalues of unitary operator are complex numbers of moduli equal to 1. That means the modulus of eigenvalues of unitary matrix is equals to 1. The eigenvalues of symmetric matrix are real and they form orthonormal basis. The eigenvalues of symmetric matrix and Hermitian matrix, they have same properties. Almost all they have same properties. And skew symmetric matrix and anti-Hermitian or skew Hermitian matrix, they have similar properties. The eigenvalues are purely imaginary or 0. So yes, there is another question. This question appeared in Central University exam, and this question is also available in a Zetley book. Zetley Quantum Mechanics by Nuruddin Zetley. You can find this problem there. Consider a particle whose matrix is given by this one and is lambda I7i minus 2 and eigenstate of H. H is Hermitian. So if till now we thought that any measurable quantity can be represented with an operator. For example, the examples for operators are position, momentum, energy, kinetic energy like this. We can also write any operator in the matrix form. So as an example, here the matrix is given like this. H is an Hermitian operator here. H is an Hamiltonian operator which is given in the form of a matrix. So you are asked to check whether the wave function lambda is an eigenstate or not. That means we have to check this condition. H acting on psi is equals to some eigenvalue into lambda. If this eigenvalue condition is satisfied, then I can say that the given lambda is an eigenstate. H acting on lambda. What is H here? So 2i0 minus 1 1 0, sorry, this is minus I, and 0 1 0. This is an operator in the form of matrix, and this is acting on, if this is acting on a given wave function, given state vector, this one. So do the matrix multiplication here. So 2 into I, 2i first term, and second term is minus 7 and the third term is 0, and second here minus I into I, you will get 1 plus 7i minus 0. This term is 0, 7i and 0. So you will get the function is like this one, 2i minus 7, 1 plus 7i and 7i. So when H is operating on psi, you got this one. This is not equals to eigenvalue, some eigenvalue into psi. So this is not in the form of eigenvalue equation. Therefore, the lambda is not an eigenstate. Now we can check the given Hamiltonian matrix is Hermitian or not. For this, you have to prove H dagger is equals to H. Then I can say H is Hamiltonian. H dagger is nothing but the transposed conjugate of that matrix. First of all, write down this is H. The transpose means rows will be written as columns like this. This is minus I 1 0 0 1 0. So this will become 0 1 0. 2 I 0 minus 1 0 0 1 0. Okay, and write down the complex conjugate here. That is 2, and this can go 0 I 0, and this is minus I, this is 1, and this is 1 0 0 0. So which is not equals to H. That means the given matrix H is not Hermitian matrix. The lambda is not an eigenstate and H is not an Hermitian matrix, Hermitian operator. And there is another question, just 2015. It is easy to write this one also. Here in this problem, the value of operator H, the operator H is given like this: minus 1 1 plus I into 0 1 minus 1 0. We can write the Hamiltonian in this form. So now he is asking that the eigenvalues of H are. So here I can write this Hamiltonian in terms of a matrix. So here the basis is given as 0 and 1. So when you have two states, the first I can write the combination of these two states. The first one becomes 0 1 0 0 and 0 1 state, and this will become 1 0, and the other one will become 1 1 state. So just write this Hamilton in terms of a matrix. This is 0 0, so there is eigenvalue 1, so it will be written as 1, and 0 1 is this one. 0 1 is having eigenvalue I, and 1 0 is having I, and minus 1 minus sign is there, so minus I here. And what is else? 1 1, so 1 1 is having minus 1 value. Okay, finally I will write H value here. H is 1 I minus I minus 1. So this is the Hamiltonian in the matrix form. Here 0 and 1 are orthonormal states. When you have two states, I can write it as a 2 by 2 matrix, like 0 0 0 1 1 0 and 1 1. So this is Hamiltonian. Now how to find the eigenvalues of a matrix? We know the characteristic equation H minus lambda I. The determinant of H minus lambda I is equal to 0. So this equation is known as secular equation or characteristics equation. So the character from this characteristic equation you can calculate the eigenvalues. So 1 minus lambda minus 1 minus lambda, that is equals to 0. So this is the characteristic equation, and from this equation I can write, 1 minus lambda into I will write minus here, and this will become 1 plus lambda minus I into I into I is 1, and there is a minus. I into I is minus 1, and there is a minus, that is plus 1, and already there is minus. So from this I can write, when you solve this one, you will get lambda square minus 1 is equals to 1, or lambda square is equals to 2, and lambda is equals to plus or minus root 2. Therefore lambda is equals to plus or minus root 2 are the eigenvalues of given matrix. So option C is the right option. This is a CSIR question which appeared in December 2018. Here the question is, one of the eigenvalues of the matrix e power a is e power a, where a is this one. The product of other two eigenvalues of e power a is given, and e power a is a matrix which is a 3 by 3 matrix. Since a is a 3 by 3 matrix, so e power a is also 3 by 3 matrix. So 3 by 3 matrix will have 3 eigenvalues, lambda 1, lambda 2, lambda 3 are the eigenvalues. And I know the formula, that is trace of a matrix A will be equals to the eigenvalues, sum of the eigenvalues, lambda 1 plus lambda 2 plus lambda 3, and det of that matrix will be equals to the multiplication of all eigenvalues. And there is another formula, det of A can be written as e power trace ln A, or det of e power a. If a is replaced with e power a here, you will get e power trace a. Please keep in mind these are the four formulas. Now what is the question here? The product of other two eigenvalues. One eigenvalue here is e power a. What are the other two eigenvalues? Now I will try to write det of e power a. Det of e power a is the product of three eigenvalues, Let me call the eigenvalues are alpha 1, alpha 2, alpha 3, where lambda 1, lambda 2 as eigenvalues of A, and alpha 1, alpha 2 are eigenvalues of e power A. So data of a matrix is equals to product of eigenvalues. One eigenvalue is e power A. So one eigenvalue is e power A and alpha 2, alpha 3. So he is asking that the product of other two eigenvalues. So what is alpha 2 into alpha 3? Data of e power A is this one, and we have calculated that data of e power A. Let us try to calculate data of e power A from this formula. Data of e power A is nothing but e power trace of the matrix A. Trace of the matrix A. So what is that? E power trace of A. Trace of A is nothing but sum of the diagonal elements here. So that is simply A only. Trace A is nothing but A. So that e power A is equals to e power A. And we got that e power A is equals to e power A alpha 2 alpha 3 from the formula, from the definition, and from the given condition we got e power A. So on the LHS side I can write e power A, and this is written here, and this is 1. So this equation is satisfied. E power A is equals to e power A into alpha 2 alpha 3 when alpha 2 into alpha 3 is equals to 1. If the product of the other two eigenvalues is equals to 1, then this equation is satisfied only when alpha 2 alpha 3 is equals to 1. Okay, so the answer is D. Yeah, that's it for this lecture. I hope you like this session. Thank you for your attention.